Now, the interesting thing about Unit 3, we talked about acids and esters. And so we have an acid and an alcohol forms an ester. This chapter, we're going to have an acid and an amine. They're very similar. So, as most of you remember, ammonia is a simple amine, and it looks like this, and it's sort of similar to water. Okay, there's an electrophilic atom, in this case nitrogen as opposed to oxygen, and so you have similar characteristics to water, and then we get into more complicated and similar to alcohol. Now, it's not as electronegative as oxygen. Brings the most electronegative, and if you go away from fluorine, electronegativity drops. That is further away from fluorine. It's not as strong as oxygen. So the influence of OHs, whether it be with an ester or an alcohol, is stronger than with the nitrogen version. Still there, it's not as strong though. In fact, I was just talking about Parsons ammonia. If you want to clean things, frequently they sell Parsons ammonia in the cleaning section of your grocery store. And that's basically ammonia gas dissolved in water, ammonium hydroxide. And it is great for cleaning grease because it is basic or alkaline and it saponifies the grease. Does a really good job. Okay. Now, nitrogen products are extremely important. They're ubiquitous. They're really important biochemically. Our body has a whole bunch of varying versions of nitrogen-based chemicals, proteins, enzymes. A lot of the plant-based alkaloids all have heterocyclic nitrogen parts to them. So nitrogen is really an important part of our biochemical maze of chemicals and stuff. A lot of drugs have a nitrogen, like morphine, has a nitrogen component to it. So they're really important. Okay. Now, like alcohols, remember, are primary, secondary, tertiary, so are amines. And they're very similar in terms of primary alcohol has two hydrogens coming off of that carbon with the OH group. With nitrogen compounds, it's the same thing. Two hydrogens are coming off that nitrogen, so it's a primary amine. And then similarly, secondary amines and then tertiary amines. And then we're also going to learn about something called a quaternary amine in this unit as well. Okay. There are two ways, like always, two ways to name our chemicals. There's the common way, common name, and then there's the IUPAC. As far as a lot of times we use the common names more, and it depends on what you're looking at. Are you looking at a technical a paper put out by the American Chemical Society, or are you reading something in TikTok or something like that? I mean, it varies a lot on which they're going to be using. We're going to learn both versions like we normally do. Okay, so what they do is the base is an amine. Then they name the groups hanging off of it. So in this case, we only have one, and that is all right, why doesn't this work? All righty, let's stop this for a moment. Okay, so getting back to naming, this will be the common name. So off the nitrogen, we can have three different groups to name. Okay, and you just name them up to three. If it's hydrogen, you leave it blank. Okay, so and this one we've got just a methyl group, so it's going to be methylamine. We can have two methyl groups, dimethylamine. You can have different groups naming as well. And for example, this has got an ethyl group and a methyl group, so it would be ethyl methylamine. Very simple. Also, E comes before M, the typical naming deal. So you want to put alphabetically put them in the right order. Now, as far as non common names, right? Using IUPAC, we're going to use the NH2 as a branch. Okay. So in this case, the backbone is going to be propane, 3-carbon backbone, and it's on carbon number 2. So it's not going to be the main deal. It's going to be a branch. Secondly, when you're looking at things like butanol, the butanol is going to be the main backbone with a branch on carbon 1, 2, 3, 4. Carbon number 4 is a branch. Okay, so it's a little different than we've done before. Typically naming, as always, I've got 3 parts. We've got the backbone, we've got the functional group name, and then we have branching. So that's exactly the same. Okay. We can also name it as an amine. Okay, so again, we look at the primary backbone. So the main functional group is going to be amine this time. And in this case, we have nothing off the main primary backbone. So it's going to be 2-amino pentane. Here, the main backbone is going to be 1, 2, 3, 4, 4-carbon backbone. And it's the buta. And it's an amine off of carbon number 1. And we have a branch this time off of carbon number 3. So it's going to be 1 amino, 3-methyl butane. Now, what's different about having a nitrogen in there is you can have a branch off the nitrogen as well. And we were talking about alcohols and all that other stuff. There was no branching off that, but nitrogens would have a branch. Okay, so notice up here, we've got a branch coming off of that nitrogen, a little methyl group. Okay, so we have to tell it in the name what that is. And it's distinguished by an uppercase N italicized. So in this case, it's going to be N-methyl, but you can have 2 others on there as well. So it's going to be N-methyl. And then we go to a branch. And there are no branches off the primary backbone. And then we're going to go to naming what carbon the nitrogen group is off of. Will be carbon number 2. So it's going to be 4 carbons an amino group. And it's going to be on the amine is going to be a methyl group. Yeah. Yeah, like the one I have up here would be name it as an amine. If it's this is naming it as a branch. You've got in this see the problem is what happens when you have multiple functional groups. This has got an alcohol and an amine on it. So you can take a whole course on naming. It can get real detailed. So which one takes priority? And in this case, the alcohol takes priority. So we're going to name it as a base alcohol with an amino branch on it. Here, main molecule is an amine. There's nothing else to call it alcohol or acid or anything like that. It's just an amine. So the main backbone is going to be the functional group is going to be on the main backbone, which is the 4-carbon backbone here. So then you have to say what carbon is the functional coming off of, and then is there another branch? The typical name we go through. So this is a little different. This is not as straightforward as all the other ones we've done. They've been really straightforward. This can vary a little bit, especially when we get into if there's a branch off the nitrogens, because you can have like if we had that, for example. Okay, so it's that alcohol, 1, 2, 3, 4. It's 4-carbon primary backbone. So it's going to be a buta. And it's a butanol, carbon number 1. And it's got an amino group on carbon 1, 2, 3. And it's got 3 methyl groups coming off that nitrogen. So we're going to have a NNN trimethyl 2 amino butanol. Okay, does that make sense?
But still kind of, so we're just looking at it like it's a methyl. So it has the amine, the amine is in the tank, right? So which way would be the correct way to? And say if it was a question on this.
On the one on the left here?
It could be either the N-methyl 2 amino butane or the 3-methyl 1 butane.
The examples that are on the slides, like the one that was given is correct, or the one that you wrote is correct, like for if we had a question on the chest.
These are sort of not quite the same because the one on the right's got 2 functional groups. It's an alcohol and an amine.
About the one that's like on the example on the slide itself. On the left.
Yeah, the slide to the left. See how slide it says one way and then wrote it another way.
Oh, yeah, I see what you mean. Joel, what would you do in this case? He teaches the year-long organic class.
Sure, we do teach them. So, when it gets to the two styles, both are valid. based on how alcohol has been introduced to the class. The second one, the handwritten one, is more consistent with what we have learned in the past, so I would ask students to say. The IU pack actually has the names on the very, the bottoms, they don't change the family name. So we will just go with that, but in real life, both of them.
Okay, so on a normal test, I get partial credit for naming and stuff. The more, well, this is the last unit before we get to pure biochemistry, but on this one, on a test, I would be much clearer on only having one answer. Yeah. They're both IUPAC. The problem with organic chemistry, there are millions of them around, and they use them in all kinds of industry. And the industry tends to stick with kind of their own industry names, like the common name. There's the ag industry, and they have their pesticide names and all that junk. There's the food industry, and they have their way of naming stuff. And then there's the quote unquote official name, which is sometimes yet again different. And next time you have a prescription drug, like I was telling you before, take out the paper that comes with it, and it'll tell you the IUPAC name. And it's usually about 5 lines long, and it's crazy complicated. That's why you can go to a website and there's a zillion rules on this stuff, and it's like he was saying, either probably will work fine. So I'm glad actually you were here, Joel. Answer this. Okay, all right. Yeah,
When you use the N, the italic N,
yeah.
when do you use that?
Okay, the question was, when do you use the italic uppercase N? That's when there's a branch off the nitrogen. See right here, there's a methyl. And right over here, there are 3 methyls. So each time there's a branch off the nitrogen, you say N. And then this has to correspond with the number of the branches off the nitrogen. So if there are 3 branches, you have to say what it is. In this case, they're all methyl, so it's going to be trimethyl, but it could be ethyl methyl propyl. I mean, you have to signify for each N, you have to know what it is. That makes sense?
Yeah.
Okay, so these are non-aromatic, aliphatic, and these are aromatic. So like what we've been doing before. Yeah, exactly. Yeah. Yeah, the N signifies there's a branch. Then you have to say what the branch is. Okay, like a previous chapter on acids, we had benzoic acid as the simple aromatic compound. And then we had toluene when we had the methyl group. And in this case, we're going to have aniline. Okay, so we have what's going to be the benzene base, and then let's look at this guy here. So that's going to be our base. And we've got a branch off the nitrogen, so we have to have an uppercase N there to signify there's a branch off the nitrogen, and then we have a branch off of the ring. Okay, and at that point, let's stop for a second. We have some other business to do. As I told you before, I'm being evaluated today. So guess what? We have student evaluations. And Dr. Wong needs to do it, not me. Okay, go ahead.
Professor Ferguson. So what I'm gonna do is I will be handing out the students' evaluation forms. And these are so that we can give feedback to our faculty members to improve teaching. And what I can say is that whatever you like about the class, very likely because, people in the past have suggested those recommendations on what they like, what they hope to see, in class. So I'd like to invite you to be as specific as you can. If you really love something, call it out because Professor Ferguson is going to receive these, but at the end of this semester or probably beginning of next semester. So until then, probably things would have passed and would know what was that about. So just be specific. If there's anything that you would love to see improved, be specific as well, instead of like, oh, I don't understand this, and that would be good. What could have been done? Because these things, if they're implementable, then the next semester of students, they would benefit from the feedback. So after you're done, go ahead and turn in your evaluation form in the front. If you have any questions, feel free to ask. Yes.
Course code?
The course code, that's a good question. Keep that for now. The course name Chem 306. Oh. Yeah, of course, so it's kind of like how you added to this class that the five code code.
Thank you. I see it. It's on canvas. Thank you.
17,
226.
226. Okay. Put that down.
Thank you.
If you're done, feel free to just point the file. couple of minutes if you need to wrap anything up. And the more specific the comments, the better. Professor Ferguson will see these earliest. Usually it's at the beginning of next semester sometime, so I think that definitely helps. We're waiting for any points. Then have a hand raised if you're still working on the evaluation. Okay, no worries. 306 was one of my favorite classes to teach. Fun class. I hope you guys are feeling the same way, more or less. Have to run off to my own class, so if there's side of these comments, feel free to email me. Find anything that I could add on to the feedback. Anybody else? Okay, if not, I wish all of you the best of your rest of the semester, and this is probably your last semester class. Is it? Okay, so I hope you guys end with a bang, which means ending with a good celebration, not anything bad, but all good things, okay? All right, have a great rest of the semester. Okay.
So.
How was it?
I was fine to like save my like the own anywhere, like I still possibly any.
Oh, no. I felt the first question, like, how can it? I think it's, and I feel that I
Yeah, I really appreciate it.
I think everybody you're done. I feel like you're done. I'm just. I want the second one back. There was where you wait. He's kind of first.
Now I'm all nervous.
It's okay, we all wrote good things about you.
But normally, when we get into naming, it's very straightforward, right? Till today. Okay. And of course, I didn't pause the recording. So. Okay, back to the aromatics. Okay, if it's got um, an amino group hanging off of it, it's not called amino benzene, it's called amylone. Now to name this, get over here. So the aniline is going to be the base. And then we have stuff hanging off of that. So we've got a branch coming off of the ring at position number 2. And that's an ethyl branch. And then we have a branch off of the nitrogen. So we need to throw in the uppercase and italicize to indicate there's a branch coming off of the nitrogen. So the nitrogens add another layer of complexity when you start talking about now, the important part is the naming. The reason why I focus on the naming is so you can focus on the structure. That's why before we have 2 alternate names, we've really focused on the structure to get that. So the goal there is to focus on the structure. It's just with nitrogen involved, it's a little more complicated, that's all. Okay. Now, when we look at primary, secondary, tertiary amines, we are going to have some hydrogen bonding involved because the nitrogen is electronegative. So it's going to pull that electron cloud from the other atoms around it. So it ends up being partially negative, just like with the oxygen, partially negative. Not as strong as the oxygen though, because it's oxygen is closer to fluorine. Okay, so if you've got either water around or something else that's polar, it'll dissolve in it because itself is polar. Now, the same thing applies. If we have a big, long backbone, what's going to happen is that backbone of 7 carbons or longer is going to kind of take over the polarity of the nitrogen. Okay, so that is going to be less soluble in water than these guys here. Because the long backbone, the long non-polar backbone is going to take over. Even though itself is not polar, it's got London dispersion forces that make it slightly polar. So think of 7 carbons. Seven carbon as the breakpoint. Okay. Another problem with amines is we've got something called steric hindrance. We've mentioned this a little bit before, but when you have structures around the nitrogen, it's going to prevent other atoms from getting close to it. And that's again called steric hindrance. So its effect of hydrogen bonding is less than if we didn't have these R groups around it. Now, some interesting things about nitrogen compounds. There are 2 smelly things around in our environment. sulfur compounds and nitrogen compounds. Sulfur compounds, in fact, natural gas, methane, is odorless. And the problem is, if there's a leak, you can't smell it. So what they do is they put H2S in it, put a sulfur compound in there, so it's stinky, so you know there's a leak. Nitrogen compounds are even stinkier. They even name them, like this guy here. It's got a four carbon backbone and it's got 2 amino groups, so it's 1,4-diamino butane, but its common name is putrescine, after putrid. So when decaying animals are smelly, there are 2 reasons why. Putrescine and cadaverine, and they're both nitrogen amino groups. And they're really stinky, hence the name. But the IUPAC name is very simple. Got a 4 or 5 carbon base, with a couple of amino groups. But boy, does it smell. Okay. Now, nitrogen compounds act as weak bases. Now, from 305, we talked about acids and bases. Acids, remember, dissociate a H plus. Bases dissociate an OH minus. Or the nitrogen can grab hold that nitrogen and water molecule becomes one. And it gives off that. So it doesn't give off a hydrogen hydroxide ion directly, it's indirectly by binding up with the water and kicks off an OH. So when this happens, you end up with that's where the base properties come into play. Now, when you go to the store and you see ammonia, none of it is NH3. It is all NH4OH because it's always dissolved in water. So this reaction here happens. Just like that Parsons ammonia I was talking about earlier. If you read the little active ingredients, this is NH4OH, ammonium hydroxide. Okay. So in water, this is what happens. You have a pH that's negative. Actually, when you have a pH less than 7, it's acidic. What happens is the H plus bonds with the nitrogen. And we end up with H from the acid. Okay, how many electrons does that have? H plus. Okay, it's got a neutral H, it's got 1 electron. What does an H plus have? How many? Hmm? None. That's right, 0. Because a plus means we've lost an electron and there's only 1 to lose. So that means there's the hydrogen plus ion, the cation, has no electrons. So it wants to become more stable. So what happens is it bonds with one of the pairs on the oxygen. And the charge is also plus. So acid and water looks like that, not that. So like we did before, we have a weak acid in acidic conditions, no reaction. A weak acid in alkaline conditions, we end up with the acid salt. Amines in acidic conditions, we end up with the salt also, only it's called ammonium salt. In pH of alkaline greater than 7, it's no reaction. You need to know these. This will be on the test. Every test I've given in the last 19 years or so. Now, this is important because you can manipulate biochemicals by changing the pH. For example, if you wanted something to be dissolved in water, if it's ionic, it's going to dissolve in water. If it's non-ionic, it won't. So the idea here is we can make drugs. Our body is basically water-based. So to get drugs to dissolve or move around our body in the bloodstream, we need to make them more motile, okay? We need to make them more ionic so that the water can carry it around. So a lot of times when you look at, for example, morphine. Morphine comes as the sulfate because it's a salt, it's ionic. If you inject straight morphine into a muscle, it'll sit there for a long time. But if you inject the ionic version, it's the blood carries it around your body. Now, when I was a little kid, I'm talking about like 3 and 4, I had really bad asthma, and they didn't have any histamines at all in those days. But what they did is they give you a shot of vitamin B12 in your butt. And it was an early version of vitamin B12. It was very non-polar. So the motility of that non-polar vitamin B12 stuck around for hours. I could not walk. Remember, my dad used to take me to the, it's called Woolworths, it's not around anymore. And he'd buy me these little chips, you know, those little tiny ones you get around Easter, to take my mind off the fact I couldn't walk. And that happened for years. I'd go once a week. It was awful. And so they improved it though. In fact, that was a take-home question I used to give frequently, is I'd show the structure of vitamin B12, very complex, and I'd say, make this more soluble in blood. What would you change? What function? So you go through all the functional groups and figure out how can I make these functional groups ionic? That would be what you do. Okay. So here we have strong acid. It's going to bond to that nitrogen in the amine. We're going to end up with the ammonium salt. So we take nitrogen, and when it becomes a cation, a positive cation, it becomes ammonium. Okay, and this is what I just mentioned. Okay, so we have pH less than 7. What happens is the hydrogen from the acid goes on to the nitrogen. In fact, the name of that bond is called a coordinate covalent bond. A very specialized covalent bond. That's where something with no electrons bonds with something with excess electrons. And when we name the ion, we're going to have ammonium in the name. The anion is going to be last. So this part here is going to be the ammonium part. And we've got three branches. We have an ethyl and two methyls. So it's going to be ethyl, dimethyl, ammonium bromide. Naming gets complicated in this unit. Gets even more complicated in a little while. Okay, so here's morphine. Little nitrogen here. So if we make the morphine salt, morphine sulfate, it becomes ionic and able to call it motility, more motile in the blood. If you have an ammonium salt and you throw it in a basic or alkaline environment, what happens is the OH is going to grab hold of that H, pull it right off, and form water. Now, I mentioned earlier we have primary, secondary, tertiary amines, and then I also said there's quaternary amines. Those are named quaternary ammonium salts. And basically, that's when you've got four groups hanging off the nitrogen. Hence the quaternary. Now, the important thing on this is they're independent of pH. They're independent of whether it's acidic or an alkaline environment. They're always the same. So it's independent of pH. From a biochemical perspective, choline is a really good example of a neurotransmitter. It's also a good example of a quaternary salt. So it looks like this. It's got a 2-carbon backbone. Nitrogen has got 3 methyls hanging off of it. And at the other end is an alcohol. This is what's in lecithin. If you remember from unit 3, lecithin has got choline forming an ester of phosphoric acid on the very third one down, third carbon down. Now, choline is a really important neurotransmitter. It allows the synapse to function. No neurotransmitter, synapses don't function. So, if you can, and this is the way muscles work. You've got a synapse and you've got a receptor on one end. You send the neurotransmitter across the gap and it lands on the receptor, and that receptor kicks off the neuron. Then there's another enzyme that comes along and pulls the neurotransmitter off the receptor so it's available again. So organophosphate pesticides are choline esterase inhibitors. Choline esterase is the enzyme that pulls choline off the receptor. So the nerve stops functioning. Now, this is a big deal if that nerve happens to be on your lung, working your diaphragm, or your heart, And that's a major pesticide used in the 50s, 60s, and 70s. When I had my farm, we used to spray this one stuff, organophosphate, and we had to kill navel orangeworm on the almond trees. The problem is we had to spray it at the same time we were pollinating the almond trees, the bees. We had this dilemma. How much pesticide to spray versus how many bees are we going to kill? We need to minimize the bee kill because we didn't want to hurt them because they're fragile. Nowadays, it's not even used anymore. It's totally outlawed. But in those days, this was in the 70s again, things change. Yeah, we killed off probably 5% of the bees in the hives. It was, in these hives, we had 30 or 40 hives on the orchard. And there were about this many bees for each hive. Now there are thousands of bees, so it's not a whole lot, but still some died. It was, by the way, cholinesterase inhibitors, a bad pesticide. I almost got killed because of cholinesterase inhibitor pesticide. When I was loading up this pesticide, I had a walnut ranch and it had walnuts and almonds on it. And we had this giant sprayer, had a 500-gallon tank on it. And when you mix up the pesticide, it comes as a concentrate. So I had to climb up this ladder, and it was pretty high up, and I had to dump this pesticide into the big, tank. And what happened is it sloshed out onto my leg. Now, had I not been wearing a rubber suit and a respirator, Mr. Ferguson wouldn't be around right now. I would have died probably within 30 seconds. And there's an antidote for it called atropine sulfate that you can inject. But I would have been flopping on the ground and all my men were didn't know about the atropine sulfate. So, but anyway, yeah, it's really bad stuff. Works really well on mammals as well as insects. And what it does, it stops that neurotransmitter from being lifted back off the receptor. So if you can kill that cholinesterase enzyme, that synapse is not going to work anymore. So anyway, that's the way old-fashioned pesticides used to work. Okay. Okay, now I'm going to, let's see, what time is it? It's 1:30. I'll talk a little about amines. Now, last unit 3, we talked about esters. Esters were alcohol, acid together. What if you have an acid and an amine together? Well, that gives you an amide. So it's very similar to an ester. Similar. Only there's a nitrogen instead of an oxygen there. So it's going to be, instead of OCO, it's going to be OCN. And the O is going to be double bonded O. Okay, so this is OCO. And a double bonded O. This is going to be a OCN. So we've got 3 situations. We've got OCO, oxygen is single bonded. We have OCO again, only the oxygen is double bonded with the ester. And we have OCN, where the oxygen is double bonded again with the nitrogen. Now, the amide is the basis of protein formation. An amino acid ties to another amino acid via an amide bond. Or if you're in a biology class, it's called a peptide bond. But in organic chemistry, biochemistry, it's an amide bond. And you form them very similarly to the way you form an ester. 3 ways form an ester. Theoretically, in 3 ways you can form an amide, except that the alcohol. Remember the least yield was the one with acid plus alcohol. That was the least yield. Okay, with the amide, the yield is so low, they didn't even say it works. It's tiny. So really, there's 2 ways to make an amide. With the acid chloride and with the anhydride. So when we have an amide bond, like I did before, we have the acid side, we have the amine side, and we have a primary backbone, secondary backbone. So this was one, the ester. So on the acid side is the primary backbone. On the alcohol or amine side, it's the secondary backbone. Now, as with esters, the anhydride is the acidic side. So then we take the anhydride plus an amine, we get an amide then. So just like esters, acid chloride and hydride are the two main ways you make an amide. So the acid chloride, highest yield. We have the amine. That's going to substitute for that chlorine, giving you HCl plus the amide. Now, in this case, it's a simple one because we just have hydrogens coming off that nitrogen, but we can have methyls, ethyls, propyls, anything like that can come off that nitrogen as well. So within the naming of the amide, remember how ester naming was kind of a pain? This is more of a pain because you have to account for the nitrogen branches as well. Okay, you've got to have a hydrogen on the nitrogen for this to work. If there's no hydrogen, it's not going to work. So for example, we have a tertiary amine. What's going to happen is it's not going to form an amine, it's going to form the salt instead. Okay. So, let's see what time, 1:36. Let's stop here. Because this amide formation, amide reactions are more complex than ester reactions. Also, the naming is a pain as well. So there's quite a bit to this amide stuff. Now, this is going to be, I'm going to do the test the same way I did the last one. You know, take home for reactions and then an in-class test where you match up, you know, structure, naming, etc. Okay. You can spend more time on the reactions. Okay, so I want you to make sure you have your pre-lab done for Tuesday, folks. Make sure the pre-lab is done. the file you're gonna download is off of, Canvas files, lab related at the very bottom. You need a pre-lab for that. Let me show you again.